Let's check over our answers for the energy pie chart practice problems. A ball is held above the ground, and then it's dropped so it falls straight down. We're looking at before it hits the ground only. At the beginning of the motion, the ball is held above the ground. It's not moving, it's just off the ground, which makes me think gravitational. It's released, and it starts to move. It's still off the ground, mostly off the ground. If you look, it's not halfway, it's most of the way. So that means most of my energy should be gravitational. The rest is kinetic. I know that it's moving, so that has to be the only other energy. As it moves all the way down, before it hits the ground, it's just a millimeter off the ground. It has very little, if any, gravitational and mostly kinetic energy. It's only moving at this point. Here we have a wind-up toy. It's wound up so a spring is compressed inside it and it allows it to move across the table. It starts to walk and then it comes to a stop. In this example, the arrows tell us what's happening. The rabbit's moving quickly, then it slows down, then it comes to a stop. At the beginning, what's driving, what's causing it to move is the compressed spring. So we have elastic energy. It's moving forward, so we have kinetic energy. We're dealing with qualitative pie graphs, so I'm just going to say it's about equal amounts. As it moves forward, however, we know that the rabbit slows down. We also know that that spring is unwinding itself, so there should be less kinetic and less elastic. As the rabbit rolls or hops across the table, it's also creating thermal energy through friction and sound energy as it makes a collision or as it rolls across the table. This accounts for dissipated energy. Remember, you can lump together things like thermal energy from friction and sound energy together if it's just being dissipated. That rabbit eventually comes to a stop, which means all of the energy has been dissipated. All of the elastic energy turned into kinetic energy, allowing the rabbit to move. As that kinetic energy caused friction between the wheels and the table, that energy dissipated all the way through. We started and ended with the same amount. However, it's just in different forms. Number 3, a baseball's thrown up in the air and then falls back down. We know that when you throw a ball in the air, throw any object in the air, it slows down due to gravity on the way up, stops, changes direction, and then speeds up on the way back down. We can use those observations to help us understand the relative amounts of different forms of energy. At the very beginning, the ball's being thrown. It's only moving. It's not off the ground. It's just moving, only kinetic. As it gets higher, it slows down on the way up, so we're going to have less kinetic energy because kinetic energy is directly related to velocity. If it slows down, I'm going to have less kinetic. It's also much further off the ground, so I have less kinetic energy and mostly gravitational. I know it's mostly gravitational because it's almost at the maximum height. At the maximum height, it stops moving up and down. It only has gravitational energy. On the way down, we see it's about halfway. So that means it's half gravitational because gravitational energy has to do with the height and mass of the object. It's halfway off the ground, so half of its energy is gravitational. The other half has to be kinetic. And right before it hits the ground, it's going to go all the way back into kinetic energy. All of that energy is going to turn right back into motion energy. A ball rolls to a stop on the floor. So we observe at the beginning the ball is moving fast, then it slows down, then it comes to a stop. It's on the floor, so we don't have any gravitational energy. It's moving, so we do have kinetic energy. That's all we see. As it rolls across the floor, it creates thermal energy. It creates sound energy, that dissipated energy. That's what takes up the room because we only have so much energy. It takes up that room in that pie chart, leaving us with only a little bit of the kinetic energy. It's still moving, but not as fast. At the very end, it's no longer moving. All of that kinetic energy turned into dissipated energy. That ball gave off thermal energy as it created friction, and as it rolled, it made a small amount of sound energy as well. A superball is dropped and bounces up and down. Create a pie chart for each position of the ball shown. At the very beginning, the ball is just being held, so it's all gravity. It hits the ground. The collision creates some dissipated energy, thermal and sound. That leaves us with only that much elastic energy to get to the top. All of that elastic energy turns into gravitational. Now it hits again, giving off dissipated energy once again. More thermal energy, more sound. So that piece of the pie keeps getting bigger and bigger. Now we only have that much elastic energy to get us up to the top of the hill again. Each time that ball bounces, that E-dis, that thermal energy, that sound energy, is going to keep going up and up and up until the ball can no longer bounce. The last pie chart on this entire motion would be all E-dis. So it would have all converted to thermal and sound energy. An object rests on a coiled spring and then is launched upward. At the beginning, the object is not moving. It's just sitting on top of a coiled spring. So we have elastic energy. It's being compressed. That's going to be released, and it's going to launch the object upward. At this point, it's almost at its maximum height, so it has mostly gravitational energy, but some kinetic energy. If it was lower, it would have more kinetic and less gravitational. At its top peak, we can tell that it's not moving anymore because there's no arrow telling us the vector direction anymore. It is stopped. So it's not moving, zero kinetic, all gravitational because it's off the ground. On the way down, the gravitational would go down because the height would decrease, and therefore the kinetic energy would increase as it moves towards the ground. Number 7 looks like the second half of number 6. A piece of clay is dropped to the floor. So at the beginning, it's not moving. It starts at all gravitational energy. As it moves towards the ground, the kinetic energy increases, the gravitational energy decreases. At about halfway through the motion, we have half kinetic, half gravitational. If it was higher up, we'd have more gravitational. If it was further down, we'd have more kinetic. It hits the ground. So all of that energy in the collision is dissipated through either thermal energy, so friction when it hits, or the sound that a ball of clay would make when it hits the ground.